Good day. This is our demonstration video for our project on the subject Discrete Structures 2 with our proposal Field Secure, a educational learning website that teaches users how various cryptographic techniques work. These 5 encryptions are categorized into 3 sections depending on how complex their processes are. So on simple, we have the Caesar cipher and the ATPash. For intermediate, we have the Vigenère and the Hill cipher, and the advanced, we have RSA. So let's visit each ciphers one by one, starting with Caesar cipher, which is, as stated here, one of the simplest and most well-known encryption techniques. So it works by shifting the alphabet into a number to the right, or if negative, to the left. We can show you here by typing out the required input boxes or text boxes. We click the cipher button and the output appears, as well as the section underneath, which displays the step-by-step procedure on how the Caesar cipher works. So let's see it here. For encryption, here's step 1. Shift the alphabet by the number. So because we have 3, the alphabet shifts from Z into A, B, C. So here it does exactly that. The C becomes Z, the A becomes D because A shifted D is D, so on. So that works. And for plain text hello, we have the mappings of the equivalent character at that index. So for H, we have, wait, where's the H? For H, we have K here, and E, we have H, and L, we have F, O, and O, we have R. And that's exactly the output, expected output. For decryption, you just have to shift back by reversing the direction of the shift or using the negative value. So for here, if we have 3 and if we make it negative, and there's also this button here which allows the user to copy the output into the input text box easily, and we cipher again using the negative. We expect the original plaintext to be output. Here works perfectly fine. Next, the ATPash cipher. It works like the Caesar cipher, but instead of a shift, it uses the reverse of the alphabet. So, show you, typing hello, click cipher, and this is the output. So here we have a visualization of the mappings and how it works. So the equivalent of A becomes Z, B becomes Y because it's the reverse. So here it maps correctly. Step 2, we get the equivalent character of the characters in the plaintext. So H becomes S, E becomes V, so on. And then step 3 is to merge the values back into a single string. ATPash cipher is reversible, so if we use the ciphertext and cipher again, we expect the output to be the original plaintext. Next, on the intermediate, we have the Vigenère cipher, which again somewhat works like the Caesar cipher with the other pages. But instead of a key number, we use um, a string or a phrase. So for example, if we type in hello and we use the key letters, hi, and click encrypt, we get this value. So yeah, for encryption, we clean the plain text, step one is very important, and convert the letters into uppercase. So if we have numbers or special characters, punctuations, then it gets removed in step one. In step two, because we have the plain text of uh, length of 5, but our key is length 2, we must extend the key to match the length of the plain text. On step 3, we use the zero indexed um, mapping of each letter in the alphabet. So A becomes 0, B becomes 1, and so on. So here H becomes 7, E becomes 5, no, sorry, 4, L becomes 11, and so on, as well as the key, the extended key. Now in step 4, we calculate we retrieve the characters. So at index 0 of the ciphertext is equal to the index that we got from the plain text on that position, and also at the key mod 26 to so we can map it back to the 26 letter alphabet. So here is it shows you the calculation. So at C0, it's 7 of H plus 7 of the key H equals 14, which is equals to O. And C1 is 4 for E, and 8 for I on the key is equal to half, which is equivalent to M, and so on until we get to the last letter, and then combine the letters again back into a single string, and we get the ciphertext. For decryption, one must simply one must simply minus it. So next is Hill cipher, which is a bit more advanced than what we've seen so far, because the Hill cipher involves square matrices and inverses and determinants, which make it more complex if manually calculating. But here we can automatically see the output and the step-by-step process of Hill cipher. So for example, if you use hello. Now here the user can either choose a 2 by 2 or a 3 by 3 matrix. If the user chose 2 by 2, then the key that must input should be equal to length 4. If 3 by 3, then it should be of length 9, because the key is converted into a square matrix that will be used later on to calculate this ciphertext. So we'll show you later. So first we must input the custom key. Now one thing about the custom key is that we have to use an invertible one, because to decrypt the ciphertext, we are using the inverse of the matrix. So if it isn't an invertible one, then we can't retrieve the original plaintext. So here, because the backend server deduced that the input key is invertible, so we must change it to an invertible matrix. So that works fine. This is the output. So on the key generation, we convert like the Visioneer cipher. There's a mapping of the index of the alphabet on each letter. So for jail, we convert that into the letters, and then we use that. We assign the value into our key matrix, which is 9, 0, 8, 11. And step 2, we must ensure that the matrix is invertible. So for encryption, step 1, because our um, plain text length is 5, but our key is 2 by 2, and it must be divisible so that the length matches later on. So we'll see here, because we chose 2 by 2, then the column matrix for the plain text must be 1 over 2. So here, it creates a series of 1 by n matrices, and if it isn't matched, then we usually fill it with a placeholder character, most commonly X, capital X. So we, like the key, we convert the matrix into the index of the corresponding letter, and then multiply the matrix. So using the key multiply by the column matrix, we get this new column matrix mod 26 for each of the column matrices that has been calculated, and then convert it back to letters, and then combine um, up to down, left to right, and we get the ciphertext as seen here, which is the same as the output. And also it respects the capitalization of each letter. So capital H, capital L. The capital B is from the capital X that has been inserted. And yep, to decrypt, we can copy and click decrypt, and expect the original plain text with a placeholder. So that works. Next and lastly is RSA in advanced. Now, before we can cipher or encrypt the plain text, we must click on the generate button here, or the user can also opt to input their own prime P, Q, and E, but they must ensure that it is a prime numbers, because primes make the encryptions more secure, because primes are unique. They have no multiples other than one in itself. We click generate. So here are the values. It automatically places in the text box. We type in any plain text, click encrypt, and this is the value. It looks weird because it isn't confined into the 26 character limit of the alphabet, but rather by Unicode, which is the standard for character encoding. So key generation first. Step 1, we calculate the n, which is p times q, which is this value, and then the Euler-Torsion function phi of n is equal to p minus 1 times q minus 1, which is this value, and then we use the e, which is predefined. It's stated here that before 17 is a commonly used, but now it's 65,000. Then step 4, we calculate the d, which if multiplied by the e must be mod by the torsion function is equal to 1. So we get that, and then place it correctly for use in the public and private key. Now for encryption, we convert the characters in the plain text into Unicode or ASCII, so H doesn't become the equivalent index in the alphabet, but rather on the ASCII mapping. Then step 2, we calculate the character of the plain text using the formula of m raised to the exponent mod this value for each character. Then we convert that character into its corresponding value into its corresponding character, and then combine the letters. So that's the output. For decryption, we just use the formula C, the character raised by the value of the mod n. So we can show that, copy it, and then encrypt. Using the same key, we get the original value back. So that's all for our proposal Field Secure, which is the educational learning tool for various cryptographic techniques. Thank you and good day.